if pressure is constant. So what that means is the constant has to actually stay constant. It will not change. So if volume goes up, to keep this whole side equal to the same exact thing as it used to be equal to, what happens to temperature?
It also goes up.
Right. If this becomes a bigger number, you have to divide it by a bigger number to remain constant, right? So, I mean, that's just like saying, 2 over 1 is a constant, is equal to 2, right? So if I multiply 2 times 3, I get 6. Well, to keep the thing constant, I have to multiply the denominator by 3 also, right? So if one goes up, the other has to go up to remain this exact same constant. But that's only true, for example, for Charles' law if pressure is constant. Is it working?
Yeah, but the camera can't read it.
Okay. The marker is bad. Okay, so let's have a quick review. Pressure, for physics, pressure will be measured in a force unit divided by a area unit. So, okay, maybe that's, what, 3 inches squared, right? I mean, 3 inches by 3 inches, so that'd be 9 inches squared, right? So if I apply 20 newtons of pressure to that 9-inch square surface area, then I'd have 20 newtons over 9 inches squared. That's a perfectly legitimate force unit, but chemists use units like this. 1 atmosphere, 760 torr, which is 760 millimeters of mercury, 101.3 kilopascals. And then we talked about Boyle's law, which says pressure and volume are inversely proportional if temperature is constant. The caveat is required. Boyle's law doesn't work if temperature is not constant. Charles' law, volume divided by temperature. So volume and temperature are directly related if pressure is constant. That means if volume goes up, if volume increases while pressure is remaining the same, temperature has to increase to make it continue to equal the constant. This number can't change. So if this one goes up, this one has to also go up. That's what directly related means. Just like if 2 is divided by 1, you get the constant of 2. To keep it all equal, you have to multiply both sides by the same factor. So 6 over 3 is the same as 2. So if one goes up, the other has to go up. Now, you can quickly see that Charles' law leads us to some trouble because temperature in Fahrenheit and Celsius can equal 0. But can we ever divide in a fraction and have the denominator be 0?
No.
No. So if we can't divide and have the denominator be 0, then what do we absolutely have to do?
Use Kelvin.
We have to use Kelvin. So the Kelvin temperature scale is the only one you can use for gas laws. And he's going to try to trick you on the test and give you Celsius, and you're going to convert to Kelvin and not forget, right? Yes. Okay, so you can't get a 0 here, so you have to use Kelvin. So how do we convert from Celsius to Kelvin?
Celsius plus the 273.15.
Okay, so Kelvin is just Celsius plus 273.15. Next week we're going to do the experiment that shows us kind of how we figured out where 0 Kelvin might be. Of course, we won't get super awesome results, but we'll get close. Well, I mean, usually we find that absolute 0 is somewhere around negative 200 Celsius, which is kind of far off, but considering our lab equipment, it's not bad. So absolute 0, where the temperature is approaching 0 Kelvin, what happens to volume? Right, when temperature goes down, volume goes down. So volume approaches what?
0.
Volume approaches 0. So when temperature approaches 0 Kelvin, volume approaches 0. And I'll tell you at MIT, like, immediately that that's not completely true these days. They've sort of learned stuff now. but that works for us, and it works within any normal temperature range that almost anybody would ever use in the lab, so it's okay. So when you look at Boyle's law and Charles' law, they independently and experimentally determined these two laws. And Charles also saw that it didn't matter what gas you used. If you do the experiment with nitrogen gas, you get a line, right? If you do it with carbon dioxide, you get a line. If you do it with any gas, and all those lines intersected right there at where we can experimentally see the absolute zero would be.
But he never made it that far.
No. I think they have gotten to like some ridiculous tiny decimal.
That's their record, I think.
Yeah. They've gotten very, very close to absolute zero. And we know the volume never actually goes to zero. But quantum theory, it's complicated at that point. I mean, that's like beyond what I ever want to talk about or think about. So if you go into very specialized fields, you might learn about that. But for everyone else, for what you're going to do, it's going to work to just use that. So when we look at Boyle's law and Charles' law, it's pretty quick that we would come up with the combined gas law, which is what?
P1 V1 over T1 equals P2 V2 over T2.
Okay, so this accounts for those situations when we're not in a perfect lab environment and we can't hold one thing constant. But if you have pressure, volume, and temperature at the beginning of an experiment, you multiply pressure times volume divided by temperature. At the end of that experiment, you can pretty much guess that it's going to be equal to the same thing. They all three might change, but if you plug them in here, they're going to be the same altogether.
So how much do you want me to record?
I'll tell you when to stop. So, combined gas law. Now, the combined gas law only works if your gases behave like ideal gases. Ideal gases. So the properties of ideal gases, molecules and atoms, have to be very small compared to the volume. And that is a pretty relative thing. So let's say we think about the molecules of gas floating around in this room. Is there a small amount of matter making up the gas floating in this room compared to the space in the room? Yes. Right? I mean, if we sucked all the air out of this room and put it in a little tank, it would easily fit, right? It has tons of room to float around. And really, you're not going to, I mean, unless you're really compressing gas, it'll behave like an ideal gas up until 1.3 or 4 atmospheres of pressure. So you can compress it a little bit. It won't hurt. And then the molecules have to be too far apart for attractive and repulsive forces. So what that means, I mean, you guys have seen that all chemical reactions are a result of shared electrons, right? That there's attractive forces between electrons and nuclei. And of course, you know, everything has valence electrons. So when two molecules come together, their valence electrons repel, right? And that's why my hand doesn't go through the table. The table's not made of much matter, but all of the valence electrons repel everything. And there's hardly anything making up the table compared to the amount of space there is. You don't want to get gases so close that nuclei of this one attracts electrons of this one, or electrons of this one repel electrons of this one. So it can't be attractive and repulsive electrostatic forces. And if you're not pressurizing the gas, you're probably going to be okay with that. Unless you have like a lot of ions or something in the gas, but not likely. And there have to be elastic collisions between the particles and the container, no energy lost. So, for example, this was hot tea when I left the house. It was 13 degrees, you know. So do you think my cup feels warm? Yes, so my cup feels warm. So this is a liquid and not a gas inside, but are the molecules having elastic collisions with their container?
Yes.
No, because my container feels hot, right? My poor cup. My container feels hot, so that means that energy is being lost every time those molecules collide with the side of the container, right? Heat's leaking out. So when the air crashes into the wall, are the air molecules losing energy? Maybe. So is the air in this room behaving like an ideal gas? There's a gray area of science for you. So you have to consider, is your gas behaving like an ideal gas? So yes, in this room we have molecules that are small compared to the available space. We haven't compressed the gas. They're probably too far apart to attract and repel each other. Okay, when they collide with each other, are they having elastic collisions? No energy loss? Probably, because if they collide, one might gain energy, one might lose energy, but no net change in energy, right? The energy stays within the system. With the walls, with us, I don't know. Maybe we don't have perfectly elastic collisions going on, so that might be a gray area. So, that's required for ideal gas. Let's keep some. That's awesome. So the last couple things before we talk about problems that we just need to touch on. Standard temperature and pressure. Liam.
Do we need to memorize the ideal gas?
Yes. You need to know the three properties of an ideal gas. Small particles compared to the size of the volume that they have to move around. They're not so close that they attract and repel each other electrostatically, and that they have elastic collisions with each other and their walls, doors, and stuff in there.
It's nice that it was already in Algebra 2.
Oh, did you study that in algebra? Really?
Yeah. Yeah.
Like these equations,
Yes.
or even the
Yep.
what? Look.
Saxon Algebra 2.
How
Saxon.
far? What lesson is that?
I don't know, maybe in the 80s or 90s.
Are the
Oh no, there's
topics
like
of
130.
an ideal gas, are they in the book somewhere?
Yes,
Okay.
in black
Well-
in the middle, like the memorize me thing.
Okay.
So it's nice I already know that
So,
formula.
standard temperature and pressure, which in a module or two, I'm going to teach you a whole new thing called standard conditions, which is evilly named because standard temperature and pressure and standard conditions sound exactly the same, but they're not. They're totally different. Isn't that horrible? But today you're going to learn STP, standard temperature and pressure. So when you have a problem that just says, this all starts out at these temperatures, pressures, volumes, and they end up at STP. What that tells you is temperature is 273 Kelvin, and pressure is 1 atmosphere. And of course, you know 1 atmosphere could also mean 760.0 torr or millimeters of mercury. So if they give you the other pressure in torr, you can just easily convert. But and you can only use 3 significant figures for standard temperature, 273 Kelvin. Standard conditions is like 293 Kelvin in 1 atmosphere. So, last thing to talk about before we do other stuff. Dalton's law. When 2 or more ideal gases are mixed, the total pressure, which I would abbreviate thusly, total pressure is equal to the sum of all the partial pressures, depending on how many gases you mix together. So this is like an absolute no-brainer, makes everything so easy with gas laws, because if you know how much pressure this gas exerts and you mix it with this gas and you know how much pressure it will exert, you just add up the pressures to get the total pressure. And we will look at that. So, fun facts about gas: pressure doesn't depend on what the gas is made of. Carbon dioxide, if you have 2 moles of carbon dioxide and 2 moles of water vapor, they have the exact same pressure as long as they're at the same temperature, same volume, right? So the same amount of any gas, as long as its conditions are the same, has the same pressure. So gases just behave like gases. It doesn't matter what chemical they're made of. So very convenient. I love that part about gases. So let us, I basically have infinite amount of lab material here. So you guys can see from the combined gas law, P1V1 over T1 equals P2V2 over T2. And looking at Boyle's law and Charles' law, there's like kind of the unnamed gas law, right? Like this is pressure and volume of temperature is constant, and this is volume and temperature of pressure is constant. But what about, they never named the one where volume is constant. So like pressure and temperature and volume is constant, right? So this is a fire syringe. I hope there's still something in there, but I'm not entirely sure. Let's see if I can, I should have brought a cotton ball. I need something that catch on fire. Maybe a tissue. If I shred up a tiny piece of tissue a lot, perhaps. Okay, so
I don't have anything. Don't ask me. I like everything I'm wearing.
no cotton balls. You always have a cotton ball, right?
No, I don't.
No?
No.
I've had students with all kinds of strange things out of their pockets when I need something, so you never know. Less often now, but generally lighters and weaponry and all sorts of fun things. Okay, so I've got little fluff here. I can get this apart. So if volume's constant, right? So once the seal is there, the volume of gas in there is a constant amount, right? Like maybe a couple milliliters or whatever, a tiny little, tiny amounts of fluff are good. Yeah, I did it the smart way this time. Okay. So, once I get it closed, it's greased in there, so it shouldn't allow any air out or any air in. So the volume of gas in there is constant, right? So when I apply pressure to it, right, it squishes it down. What would you expect to happen to the temperature? So volume's constant, when pressure goes up, what happens to temperature? Temperature is going to go up. So hopefully this can withstand it. Can you see it like start to smoke? It hits the smoke point. If you push it really hard, you can watch it smoke. You have to like put your eye down it. Can you see it? Did you get it on fire? Sometimes the boys can get it to catch fire. I can't push hard enough.
It smokes. That's so cool.
That's cool.
And it'll just keep doing it. And no, nobody can take it outside and burn up bugs, because I actually had a physics class do that once, and it's gross to clean out. And mean.
Is that what the yellow stuff is?
No, that's grease just to make sure that no air can escape or get in, because I have to hold it at a constant volume of gas. So, yep, so temperature goes way up under
What
pressure.
did you use that for?
Fun. I mean, but
It has no practical use.
Catching things
I'm
on
sure
fire.
it does. I mean, like if you need to start a fire, you can. If you don't have any other way to start a fire, you can trap a volume of gas and pressurize it and put something in there with a low flash point, and it'll catch on fire.
Because if you're stranded and you have nothing else, that's...
Yeah, I'm sure you can build a
definitely
constant
do
volume
that.
container with a piston.
Yeah.
No problem. It's the most efficient way to start a fire I can think of.
Lots
Yeah.
of kerosene.
I have a question.
That would be so much better.
This isn't really, I was thinking about this the other day. There was a soda bottle, like a Sprite, in my car, and it totally, it exploded, like, out, it didn't explode, but, you know, like, the front and the back of the soda can, it was completely, like, pushed out.
Worked out, yeah.
Because that was because of pressure, but is it because it was too cold that it didn't explode when we opened it, or because it had already gone flat? I was wondering, like, why it didn't explode, because it was so pressurized inside of it.
It probably didn't explode. There are some cool demonstrations you can do with non-carbonated liquids. So my thought here is when the thing froze, it trapped the gas in the frozen matrix, so the gas couldn't rush out when you opened it.
Yeah.
And I guess the bottle was just strong enough to withstand the expansion.
Yeah, I was like, that's why I thought, but I wasn't sure. I was like, I should ask this guy.
Yeah, I mean, it's mostly water, so it would expand when it freezes. But one of the things, I can never get this to work, but I've heard nobody else has this problem, so I've tried it lots of times. I'm not going to try it with you guys, but you can try it at home. You get a water bottle in a really, really, really cold freezer, or like you leave it in your 12-degree car, but you can't bump it. So it gets super cold, and then when you do bump it, it like instantly freezes because it's already below the freezing point. So one little jiggle causes one crystal, and then everything else crystallizes right on that.
Yeah, people do that. There's YouTube
I know.
videos. Like,
Everybody
it's
on
really
YouTube
frozen,
does
and then they just go
bang,
and then it freezes.
It doesn't work for me.
Well, it's cool.
I've tried many, many times. But people find it by accident because they leave their water bottle in the car, and then they pick it up, and it's like, whoosh, and it freezes. It doesn't explode because it doesn't expand that much when it freezes, but it just suddenly, like, goes from liquid to solid, bam.
You're a wizard.
But that's just a phase change and doesn't really have anything to do with gas laws. Even if the thing is carbonated, the gas laws aren't really coming into play there. Although the freezing point will be depressed if it has sugar or gases dissolved in it, because, you know, freezing point depression happens when you dissolve stuff in water. So, where are we? All right, so we should do all of these things. We need to look at Boyle's Law page. What other page did I hand up? Oh, 12.1. We'll do that last. Yeah, if only one of us has it, we're good.
7 minutes.
And I think I do. 7 minutes, that's okay, let it go. And review questions and practice problems, which you should probably consider first, just in case. And next week we're going to do Charles' Law and boiling water with ice. Because I can boil water below room temperature with ice. And hopefully you guys can figure out how when you read the next part of the module. If you come knowing how, that'd be fun. And since you guys are here and there are 3 people absent, if they don't watch the videos, you don't want to sit right here next week. That's the danger zone. And if you do, you want goggles, remind me. And I want goggles, remind me. So, Boyle's Law, Charles' Law, and practice problems. I don't seem to have practice problems for Module 12. Great. That's really great. Alright. No, I have 13, but not 12. Wonderful. Okay. I don't even have a book. 10. Alright, will somebody read the first review question while I try to figure out where mine are? Oh, Jolene, look, here's a paper that I didn't give you back. Here, did it die?
Nope. 6 minutes.
6 minutes. No pressure.
More like 5 minutes.
Maybe probably just for me. I'll just have to sit down next to Jenny or something. Alright. I will stand right here. Point the camera at the person who's talking, not at me, please. So, first one, and we'll start over here with Brittany. Define pressure and name 3 units to measure it.
Okay, I wrote pressure is defined as force per unit area that a gas exerts on its surroundings. And then I used kPa, ATMs, and torr.
Good. 3 pressure units. Perfect. And you could have used Newton per square inch or pound per square foot or whatever. And Maddie, write Boyle's Law in your own words.
Pressure and volume have an inverse relationship if temperature is constant.
Perfect. And that's what we're going to do today. So I always try to do the experiment for Boyle's Law one day and the experiment for Charles' Law the other day, so you really get fixed in your mind which is which. I learned if you do them both on the same day, people are like jumbled. And me too. So Lily, which laws lead to the Kelvin, we didn't talk about this, we're going to talk about this next week. Which law in this module leads to the Kelvin temperature scale?
Is that Charles' Law?
Yes, Charles' Law. And next week we'll look at how he extrapolated all those lines to the same place and came up with where 0 would be, and then just added that number to Celsius so that we could never get a 0 in the denominator, because obviously he knew 0 and the denominator is undefined. Let's see, so what general rule should a scientist follow in extrapolating data?
I don't know.
Next week we're going to talk about that. Take a guess. This is like the perfect question for you. I hate to even tell you because this is how your mind works. Like you always have creative answers for when people mess up things like this. All right, so start them off, Austin, and then we'll see.
When you have a small amount of data, you can't just extrapolate something because you don't have the sufficient amount of data. So you need to have a large amount of data in order to, kind of go along with assuming that it's going to keep going along at that rate.
Good. And next week, we're going to exactly do the wrong thing on extrapolating data. So we're going to take temperature range data over normal things that we can do, right? We can get water up to 100. We can get cold water down to 0. That's basically the range over which we can experiment in this classroom, right? So we have a 100-degree temperature range that we can work with. But with a 100-degree temperature range, can I extrapolate down to somewhere close to negative 300? No, if I take 100 degrees of data points, okay, so for me, my comfort level would be I can extrapolate 20 degrees this way or 20 degrees this way. Okay, like a fifth piece of my data I would go. Some people say you can even go as far as equivalent. So if I have 100 range of data, I can go 100 degrees this way or 100 degrees that way. But going 300 degrees this way is a big no. That is extrapolating way further than your data set allows. And we're absolutely going to do that next week.
So the answer to 4 would be stay within
You need to stay within a conservative range, a piece of the amount of data you have, but no more than the amount of data you have at least. And I would say no more than a fifth of what you have. Thank you, Brittany. Okay, so Grace, what are the properties of an ideal gas?
The molecules or atoms that make up an ideal gas must be small compared to the volume. The gas molecules or atoms must be far apart so they don't attract or repel each other, and the collisions that happen must be elastic collisions.
Elastic collisions, no energy lost when they collide with something. And under what conditions do gases behave ideally, Jane?
If temperature is close to or larger than 273 Kelvin? Is that what I wrote?
Mm-hmm.
Okay. Or if pressure is near or lower than 1.00 atmosphere.
Okay, so on the test, like he gives you no problems like this in any of the problem sets, and then on the test he gives you one of these. So let's kind of play with these numbers and decide what might be allowed and what might not be allowed based on that answer. So temperature. So if I have a gas at 273 Kelvin and 1 atmosphere, will it behave like an ideal gas?
Yes.
Yes. What if I have
No, because of the pressure.
This is within range
Okay.
where I would say yes. If it got any higher than like 1.3 atmospheres, I would start to say no. This is barely okay. But I would say yes to 300 Kelvin and 1.2 atmospheres, but barely.
10 seconds.
Okay. How about